Welcome to Introduction to Geology. I'm Dr. William Patterson, and in this video we will be talking about the formation and classification of biological and chemical sedimentary rocks. Biological sedimentary rocks include limestone, made up of calcareous organisms and other carbonate grains deposited in a sequence here and lithified, generally by calcite. Chert is a biological sediment that's produced from radiolarians and diatoms that get cemented together. Coal is an organic biological sedimentary rock formed by compressed plants. And phosphorite is some kind of previously existing sediment that becomes infused with phosphorus, usually associated with an upwelling zone, as we'll see in a few moments. Chemical sedimentary rocks, on the other hand, include dolostone, a calcium-magnesium carbonate, iron formations, which are iron oxide for the most part, and evaporites, in this case salts that are forming in semi-arid regions, to arid regions that have a supply of water. Some other examples include gypsum, seen here as crystals growing out of the white sands in New Mexico, and the halite deposits that form the salt mountains of Iran. Bringing that together here in this classification system, we see the sediment in this column, the rock name that results from that sediment, the chemical composition, and the mineral names. Starting here, biological material, sand and mud. Bioclastic sand and mud, when it's cemented together, will form a limestone. This is predominantly calcium carbonate, the minerals being calcite and aragonite. Now, aragonite is a metastable polymorph of calcium carbonate, so it tends to go away. It doesn't persist in the environment for long. It ultimately gets converted into calcite. Siliceous sediment, like radiolarians and diatoms, ultimately form a rock called chert, and it has this chemical composition, SiO2. The rocks that result are called opal, chalcedony, and quartz. Peat is made of organic matter. The rock is called an organic rock. This organic matter consists of carbon compounds resulting after proper cooking in minerals that aren't really minerals, known as coal, oil, and natural gas. Now, phosphorites are different in that they don't require any principal primary sediment, just sediment. That's the only requirement. Doesn't matter what it is, really. And the result is a calcium phosphate is going to form. We know this calcium phosphate commonly as apatite. Hardness of 5 makes up the enamel of your teeth. Chemical sediments, if there's it says no primary sediment here, that's not true. The primary sediment would be aragonite and calcite grains, as seen up here, that do form limestone. This limestone, over time, is converted into dolostone or dolomite. And the way we do this is we add magnesium to the calcium carbonate. This is done over time under heat and pressure. Iron oxide sediment results in a rock called an iron formation or banded iron formation, aka BIF, B-I-F. These BIFs consist of iron silicates, iron oxides, limonite, and carbonates. Some of the minerals include hematite and siderite. And then lastly, we have evaporite sediment that results in a rock called an evaporite. Generally, calcium sulfate, sodium chloride are the most common. So gypsum without water is called anhydrite, halite, and other salts. So now taking a closer look at these, the formation of limestone comes from bioclastic sand and mud composed of calcite and aragonite. We see that here. If you take a close look at this material, you see some calcareous algae here. You see foraminifera here. Maybe a piece of broken corona glass here, and other biogenic grains. So this is a death assemblage. All dead stuff in this image. The rock that results from the compression and cementation of this is limestone. Another biological rock is produced from siliceous sediment. So here we have radiolarians. You can toss in some diatoms, compress these, fuse them together with more silica, and you get a rock known as chert, which is made of the mineral quartz. Another biological sedimentary rock is coal. And we see here a Pennsylvania coal mine back in the early 1900s, forming in layers because the vegetation was accumulated in layers and compressed, squeezed, and cooked. And lastly, from the biological rock category, we have phosphorites. Phosphorites are a non-detrital rock forming in marine environments when phosphorus-rich materials from marine organisms accumulate. The rock is known as a phosphorite. So what's happening here is we have our previously deposited sediment, whatever it may be, associated with an upwelling current. This upwelling current is bringing nutrients from decaying organic matter in the deep sea, where oxygen levels are very low. Because the oxygen levels are low, there's little life to take advantage of this phosphorus-rich water. As soon as that phosphorus-rich water reaches the surface, it is now in the sunlit zone where biological organisms can suck it up and be deposited as phosphate-rich sediment. So this acts as a sponge for phosphorus, and these are very desirable deposits for fertilizer principally. I've been to one in Florida where you can stand next to the conveyor belt and watch this material come by as it's being mined, and you can pick out whale bones and rhinoceros bones and shark teeth and ray teeth, all kinds of stuff just goes by on this conveyor belt to be pulverized and turned into fertilizer. Kind of cool. And we have chemical rocks. Chemical rocks result from the diagenesis of bioclastic sand and mud composed of calcite and aragonite. When that happens, we call it dolostone or dolomite. Either term is correct for the rock. And again, this is a calcium magnesium carbonate. The way you make dolomite is you put your ingredients into a slow cooker, fill this with some carbonate mud, pump in some dissolved magnesium ions, turn on the heat, turn on the pressure, set the timer to a very long time, and wait a very long time, and boom, you have dolomite. Another chemical sedimentary rock is the iron oxide sediment that ultimately forms banded iron formations. So here we see bands of iron silicates, iron oxides, limonite, perhaps, probably not in this image, but hematite and carbonate. So again, these banded iron formations are commonly known as BIFs. These BIFs occur under special circumstances that have occurred a couple times in Earth history. So these banded iron formations are made by filling the anoxic global ocean with dissolved iron. This happened from the beginning of Earth history, when we had an ocean, to right around 3 billion years ago. And you see this oxygen whiffs here. These are brief periods of time in which oxygen was produced from photosynthetic organisms. Because the ocean is full of iron and completely anoxic, the iron can remain soluble. As soon as you put oxygen in that water, it's going to bond with iron and drop out. So basically the ocean will rust pretty quickly. You can't put much iron into oxygenated water. It's very insoluble. We see these whiffs of oxygen generating the BIFs. So whiffs equal BIFs. And this is the great oxygenation event here around 2.4 or so billion years ago, when we have very significant increases in oxygen and persistent increases in oxygen. And that's going to poison a lot of the previously existing life. The life that existed on Earth before oxygen is poisoned by oxygen. It kills them. So those life forms go away. And then we reach what's known as the boring billion, where oxygen levels are probably pretty stable, very little iron in the oceans. And then we reach this oxygenation event, the Neoproterozoic oxidation event. And this is the last big burst of oxygen formation. And the result is, this is when large plants and animals, things you can see with the naked eye, things you could hold in your hand and say, that's a plant or that's an animal, they come about because of this last big burst of oxygen that persists until this day. The rust reign continues until the oceans are iron-free. Chemical sediments that result in evaporites are seen here with some interbedded halite, and this is probably some gypsum bedding here. The slightly more resistant beds may be some calcium sulfate interspersed between the sodium chloride here. Organic reef development is, for me, a very interesting thing. This is one of the first things I studied as a graduate student at the University of Michigan, and I studied this area. The Bahama Banks, Grand Bahama Bank, or Great Bahama Bank, and Little Bahama Bank, and the Florida Keys and Florida Bay. So the result is this sediment and this blue coloration. This is very typical of carbonate-producing parts of the ocean and carbonate-producing lakes, this bright blue color. Zooming in, we can see that reefs are generally built in warm, shallow seas by organisms that precipitate calcium carbonate. Reefs do occur in lakes. They also occur in cold marine water, such as that off of southern Australia, but that's relatively rare compared to these warm, shallow water carbonates. So in the case of the Pacific, we have volcanoes popping up sporadically. as the volcanoes reach the surface, they begin to accumulate a ring of carbonate producers because of the shallow water in this warm environment. It's perfect for growing calcareous algae and corals. As the volcano sinks, because the subsurface is cooling off and becoming denser, that structure is going to sink down into the water column. If it doesn't sink too fast, the carbonate reef can keep up and continue to grow and keep itself in the light. And the result is we have an accumulation of carbonate of what's called an atoll, and it's going to fill up as materials washing in from this ridge here, the carbonate reef itself. The ridge is also going to produce carbonate that slides off the outer edge into the open ocean. So we end up with this stump-shaped feature here, this stump of carbonate in which this donut of active reef is going to be spilling materials into this quiet back reef lagoon and spilling off the outer edge. The result is a beautiful island. This is Bora Bora in the South Pacific, and we can see most of those features here. The living reef is here on the outer edge of the atoll. In the center here, we have the remains of a subducting volcano. It's cooling off and sinking. This back reef area is going to be relatively quiet compared to the fore reef area here. So it's being supplied with sediment, as you can see here, through these tidal inlets. So as the tides rise and fall, material is going to flow into this back reef environment and accumulate, ultimately replacing this volcanic material with fine-grained carbonate sediment. The same kind of thing happens out here, but the deltas that you see here are truncated by wave action.
Did you ever think that maybe there's more to life than being really, really, really ridiculously good looking?
Now, these guyots that ultimately form are very isolated, and some can be thousands of miles from any other similar feature. The result is this isolation leads to many of these hosting endemic species. That means they're found nowhere else on Earth. They're essentially evolutionary breeding grounds. Evolution is taking place on each of these, resulting in a new set of species. These guyots are also known as seamounts and tablemounts, and this is the bare seamount of the Pacific. These organic reefs can be more than just an ecological zoolander. They can have economic value to them in addition to tourism. In this case, we have the Permian rudist reefs of West Texas. These rudists were accumulating in association with enormous amounts of organic matter. They were subsided, compressed, and cooked to just the right temperature to generate the very valuable, highly prized oil of West Texas in the Permian Basin. We talked about the reefs forming in Green Lake, New York. Again, this is a freshwater environment with a reef formed by bacteria, Senecococcal bacteria, and we can take a look at some additional environments and some additional disasters. So here we have evaporite sediment and rock forming in a couple of locations. This is the Aral Sea of the former Soviet Union that was used for agriculture. So water was pumped from the Aral Sea to the surrounding fields. This was way overdone, and the result is today there's just a salty, dusty, toxic plain left behind. Even the farm fields that were productive in the past are too salty now to support any kind of crops. Ships are abandoned here. They're basically a ship graveyard in the middle of the desert. In the United States, we have the Great Salt Lake. This was formerly 1,000 feet deep. Due to some rapid drainage in the past through Red Rock Pass, the lake level dropped significantly, and now it's a mere remnant of its former size. It used to cover about a third of the size of the state of Utah. And today, the remnant salts within this basin are precipitating in the Bonneville region. And this Bonneville region, the Bonneville Salt Flats, host the World Land Speed competition every year. Now, this is an example of a super hyped up motorcycle. There's a pretty good movie called The Fastest Indian, which stars Anthony Hopkins. It's a story of a New Zealander who dreams of racing his motorcycle on the salt flats. So he heavily modifies an old 2-cylinder Indian motorcycle and makes his way to the United States and actually sets a record with that particular motorcycle. So cool story. Taking things up a notch, a big notch, this is a couple images of me standing here in North Africa, Morocco. Over my shoulder in the haze here, you can see faintly the outline of Spain. And here I'm in Spain on the Rock of Gibraltar, hanging out with my monkey. with Africa over my shoulder. The point of these two images is to show you how close these continents are together in this location. And this is formerly, historically known as the Pillars of Hercules. So this very narrow gap here connects the Atlantic Ocean to the Mediterranean Sea. At various points in history, this gap has opened a little wider and it's closed completely. When it closes completely or nearly completely, the water that flows into this basin that's now the Mediterranean Sea will evaporate. And we have layers and layers and layers of gypsum and halite crystals that represent those periods of time. This is known as the Messinian salinity crisis. You don't have to know that, but it's what it's called. Interestingly enough, the British in World War II had lookout posts here in the Rock of Gibraltar, located in this limestone sequence. And they were not able to figure out how submarines were getting in and out of the Mediterranean Sea, because these are diesel-powered submarines that make lots of noise. You could turn the motors off and use batteries, but they only last so long. So what the Germans were doing was using surface water currents, which are relatively low in salinity, moving into the Mediterranean, to cruise into the Mediterranean without making any noise. To escape the Mediterranean, they got entrained in the salty water that flows along the bottom of the Mediterranean Sea and out into the Atlantic Ocean. And we can see evidence of this salty, warm water coming out of the Mediterranean far, far out into the Atlantic Ocean, halfway across the Atlantic. So this is an example of thick evaporite deposits forming an intercontinental basin.
Let me be your solid dog. Let me be your solid dog, or I won't be your man at all. Honey, let me be your solid dog.